Hi, and welcome to this lecture on in-sector compressive sensing for beam alignment in mmWave and terahertz radios. My name is Nitin Jonathan Myers and I'm an assistant professor here at the Delft Center for Systems and Control in TU Delft. Today, my PhD student Hamid Masumi is going to talk about this exciting research area of in-sector compressive sensing. First of all, Hamid is going to show you that many of the standard compressive sensing techniques that are developed for beam alignment don't really work in practice due to a low SNR issue. He's going to explain in more detail what is this low SNR issue, and he'll motivate our work on in-sector compressive sensing. The key idea of this research is to design code words at the transmitter that focus energy on a particular sector. Okay, and after designing these code words, we optimize the compressed sensing sampling scheme such that the aliasing artifacts in CS are extremely small within the sector of interest and they could be large outside. So let's take a look at what Hamid has got to say.
Hello everyone, my name is Hamid Masumi. I'm a PhD student here at Delft Center for Systems and Control at TU Delft. You've probably heard about 5G wireless systems. It's a technology that goes beyond 4G and can enable cool applications such as AR and VR. Unlike 4G that uses few megahertz of spectrum, 5G radios exploit gigahertz of spectrum available at millimeter wave carrier frequencies. At these frequencies, it is extremely useful and important to align the beams at the transmitter and the receiver so that your AR and VR experience is seamless. Now, in this talk, I'll discuss about the beam alignment problem in 5G, which is performed every 100 milliseconds on your mobile devices. I'll explain a big challenge in beam alignment and discuss how we solve this challenge through compressive sensing. Now, let's first try to understand what compressive sensing is and what is the problem that we are really looking at in 5G. Now, let's consider the problem of sensing an N/N image as shown over here. The pipeline that you can see here describes the way that traditional sensing works. In these methods, all the n-squared pixels are measured, but storing all of these samples directly is not efficient. What instead is done is that the image is transformed into a domain where it has a sparse representation, which means that in the transformed domain, only few of the entries of the signal are non-zero and most of them are zero. Then these methods only store the values of the entries that are above a certain threshold. This is, for example, how JPEG works. As you can see, this is not an efficient compression method as it obtains all the samples and later discards usually most of the information in the transformed domain. In compressive sensing, however, compression is performed right in the sensing stage without needing to discard information later. Although subsampling in this case will result in aliasing artifacts, but compressive sensing can use a sparse prior in the signal or image to recover it only from a fraction of the measurements that traditional methods require. So with about an order of log n number of measurements, we can get similar performance as what we get with traditional or conventional methods. This means that with compressive sensing, we can save a lot in terms of sensing time, as well as the cost of the hardware. Today, our focus will be more on optimizing the way we sense the signal of interest for a wireless application and less on the CS algorithm for recovery. Now, here I will explain why CS is useful for 5G wireless systems. Let's consider a wireless system with an N/N array at the transmitter and a single antenna receiver shown over here. Wireless channel, which is denoted by H, models the propagation environment between the transmitter and the receiver. One such example of a millimeter wave channel is given by this picture over here, where we just showed the magnitude. in this example, let's say the top left component of this matrix shows the strength of the received signal when only the associated antenna element, for example this one with this component, is excited and all the other antenna elements are switched off. Okay, now when we take the 2D discrete Fourier transform of this channel, we end up with something which is called beam space that contains information on the strength of the received signal from different directions. For example, in this picture over here, there are two directions with significant received power. The brightest spot could be due to the line of sight path, and the second best spot could be because of the reflection from the lamppost. Note that the other directions result in negligibly small received power. As you can see, the beam space is sparse, and this is a common feature for millimeter wave channels because of high scattering at high frequencies. The big problem at this point is how do we estimate the wireless channel between the transmitter and the receiver, or equivalently, how do we estimate the coefficients shown on the beam space matrix, for example, these directions. So, if the transmitter somehow figures out these directions, it can steer its beam in these directions to increase the received power. To find these directions, the transmitter can use code words called beam training code words. Now, let's have a look at two common ways to find these directions. Alright, on the one hand, we have exhaustive beam search, where the transmitter scans all the directions to find the best direction. That is, the transmitter sweeps through each and every direction in sequence using a very narrow beam. So it first focuses its beam along first direction sometime, then moves the next direction, illuminates that direction, and so on and so forth. With this sequential approach, you'll end up with a lot of training overhead, because every time that the transmitter wants to illuminate a certain direction, it sends out a packet. And each packet occupies a certain amount of time. And if you want to wait for a squared amount of time, you'll end up with a lot of overhead. On the other hand, academia has been working on CS-based methods for over a decade to exploit the sparsity of the channel, but it hasn't found its way into standards like 5G or 1180 standard. This is because in the standard CS, the code words that are used have quasi-omnidirectional illumination patterns that spread the transmitter's energy in all the directions. For example, in this picture over here, the blue plane shows a quasi-omnidirectional illumination pattern. The received power is proportional to the inner product of the illumination pattern and the beam space. Therefore, when quasi-omnidirectional beams like the one shown here is used, its inner product with the beam space is usually small, which results in a low signal-to-noise ratio and causes CS algorithms to fail. Today, I will explain our proposed method that exploits sparsity in the beam space while addressing the low SNR issue with standard CS in 5G. Our proposed method can be integrated well into the 5G standard. So, first let's see how beam training in 5G works. Beam training in 5G has two main phases. First phase is called sector level sweep, or SLS in short. In this phase, beam space is divided into different sections called sectors, and different code words are used at the transmitter to obtain a measurement within each sector. For example, let's say that we have divided the beam space into 4 disjoint sectors, such that the first sector looks like the one that is shown over here. And a code word that focuses in this sector to obtain a measurement within this sector has an illumination pattern shown on the left. So this procedure is repeated to obtain a measurement for each of the sectors, and finally the sector that has the highest received power is selected as the sector of interest. Now, the second phase of the beam training in 5G standard is called beam refinement protocol. In this phase, the identified beam in the previous phase can be further refined to improve the received power. One approach could be based on the exhaustive beam search. similar to what we saw before, all the directions within the sector of interest are scanned, as you can see in this animation, and the beam with the highest received power can be used for beamforming. Typically, the number of sectors is really small, maybe 2 or 4, and because of having, say, 4 sectors that uniformly partition the beam space, we end up with the problem of estimating n square over 4 number of coefficients within each sector. And this is still a big challenge because we are looking at arrays that are extremely large. So we notice that overhead scales with n, and the factor of 1 over 4 doesn't really make a big difference when compared to something like log n. Considering the high overhead in this method, chipset manufacturers or mobile operators might decide to not refine the beam beyond a sector. The in-sector compressed sensing problem is to estimate all the coefficients within this green box, okay, without explicitly scanning each and every entry within that green box. Today, I'm going to explain our proposed CS-based method that uses CS measurements within the sector of interest or this green box to perform in-sector CS. All right, so here are 2 challenges that we need to address for our in-sector CS. The first challenge is to design code words that are compatible with low-power transmit arrays, which are usually low-resolution phased arrays. The difficulty here is to design code words from a certain alphabet that illuminate disjoint or non-overlapping sections of the beam space. These sections could be these 4. The second challenge is to optimize the compressive sampling such that the reconstruction of the beam space is extremely good within the sector of interest and it can be bad outside the sector of interest. Now, a common approach in compressed sensing is to go with random subsampling strategies. These approaches result in aliasing artifacts that are usually spread out in the beam space. For instance, in this picture over here, although the sector of interest, which is given by this green box, had 2 significant coefficients, you notice that aliasing artifacts spread out all over the beam space such that you don't identify the second best spot. Now, our goal here is to optimize the subsampling strategy beyond fully random subsampling such that the aliasing artifacts within the sector of interest are extremely small and they can be high outside of the sector of interest. So, to understand the sector design challenge, first let's see what is the problem with the common sectors. Here's an example of a binary code word with entries that are all 1s. When the transmitter applies this code word, it means that the same RF signal is sent across all the antenna elements. When such a transmission happens on the array, the transmitter generates a beam that is directive in nature, as you can see over here, and the direction is along the normal to the array. The 2D discrete Fourier transform of this code word shows the discrete beam pattern observed at discrete locations in 2D space. For a different code word, like the one you have on the right, you end up with a different illumination pattern, for example, like this. Now, prior work has looked at constructing sectors that are contiguous in nature. By contiguous, what I mean is that the illumination pattern is continuous in a rectangular way, as you can also see in these figures over here. Constructing these contiguous sectors that are localized to a section in the beam space using extremely low resolution alphabets is really hard. Let's see why. An interesting question here could be, can we construct binary matrices that basically have +1s and -1s such that their discrete Fourier transform look like the ones shown over here? So here the white spots corresponds to 0, and those that are colored, these ones, are non-zero. It turns out that it's not possible. You see, the code words that we have are real valued in this case because their entries are either +1 or -1. So their 2D DFT must have the conjugate symmetry property, but these sectors over here don't have this property. By this property, I mean that if these entries are non-zero, these entries should also be non-zero. All right, now I'll show you totally different sectors we proposed which respect the mirror symmetry property. So our idea is to use comb-like illumination patterns shown over here. These sectors are different from the contiguous sectors we looked at in the last slide. So they have a scattered illumination pattern where the black spots, like this one, mean that particular beam space coefficient is illuminated, and the white spots mean that there's no illumination at those spots. The interesting thing about these comb-like patterns is that they are complementary in nature. That is, they illuminate different directions, and together the collection of the directions that they illuminate covers the entire beam space. You can verify that such illumination patterns shown here respect the mirror symmetry, which makes them possible to be realized with one-bit phased arrays. But can we really construct binary code words that have comb-like illumination pattern? The binary code word that I showed you in the example of the last slide actually had a comb illumination pattern, as you can also see over here. But how can we really develop a mathematical method to construct such a code word for arrays with arbitrary n? Now, if we use a brute force method to construct such a sector, we'll end up with 16 degrees of freedom. That results in 2 to the power of 4 squared, or 2 to the power of 16 possible matrices to search from. As you can see, brute force method is not a reasonable approach for high-dimensional arrays, which usually is the case in mmWave or terahertz. So here I'll explain our method to construct such sectors through an example. First, we consider a basic binary block like the one shown over here. The basic block should be such that its 2D DFT has only one 2D spatial coefficient. For this basic block shown over here, its 2D DFT looks like the one that you can see on the top right. Next, we upsample this basic block such that the resulting matrix has the desired n by n dimension. An interesting question here is that what will be the 2D DFT of the upsampled matrix? If you remember from basic DSP, upsampling a matrix or a signal in one domain is equivalent to repetition and scaling in another domain in DFT. So here it will look like this. It's simple, right? But we are not done with our construction, because ones and minus ones here can be realized in phased arrays, but zeros cannot be really implemented in phased arrays. All right, to solve this issue, we obtained the 4 distinct circular shifts of the upsampled matrix you can see over here, such that all have complementary support structure. For example, this matrix over here is supported in these 4 indices, but none of the other 3 matrices have the same support. Now, the idea here is to combine all of these matrices by taking a weighted sum such that the result is realizable in a phased array. Also, to meet the resolution constraint of the phased array, the weights should be from the given alphabet. Here, the weights W1 up to W4 should be plus or minus 1. Now, what do you think the 2D DFT of the constructed code word over here, this one, will look like? Well, since the original upsampled matrix has a comb-like illumination pattern, and circularly shifting a matrix does not change the magnitude of its 2D DFT, as we know from the basic DSP, all of these 4 circular shifted matrices will have the same comb-like illumination pattern as the original upsampled matrix. Therefore, their linear combination will also have the comb illumination pattern as the upsampled matrix. Okay. Unlike brute force method with 16 degrees of freedom that I mentioned earlier, here we have 4 degrees of freedom, which are W1 up to W4. This is because of our construction to achieve the comb-like illumination pattern on the bottom right, this one. Also, as I will show you later in this talk, a good design of the weights is the one that results in a uniform illumination of the sector. Okay. Now that we've constructed the comb-like sectors, we can use these sectors to perform sector level sweep, or SLS, to find the best sector. So the transmitter applies the first comb-like sector, and the receiver measures the received power in that sector. Then the transmitter applies the second sector, and the receiver measures the received power within that sector, and this procedure is performed for all the sectors. And at the end of this procedure, the receiver sends the information on the best sector and the received power within that best sector to the transmitter. So here on the right, we compare the received power after sector level sweep, the procedure that we just saw, using our constructed sectors with some existing methods. As you can see, our method results in a higher received power than the other code words. This is because the other methods suffer from leakage effect due to their low resolution hardware that we've seen earlier. But our sectors are designed in such a way that they can illuminate complementary sectors even with extremely low resolution hardware. That's the main reason that we get a higher received power with the best sector using our method. Also, I should emphasize on the fact that 0.6 dB improvement that you see here can save a lot of energy in the long run. This is because, as I mentioned earlier, this procedure is performed every 100 milliseconds. All right, now that we've identified the sector of interest, the goal of our in-sector compressed sensing is to estimate all of the coefficients of the beam space at the green boxes over here without explicitly scanning through each of them. So if we were to explicitly scan through all of them, we will end up with huge training overhead, which is in the order of n squared over 4. But we want to minimize this overhead by using a compressed sensing based framework. Well, you could use standard compressed sensing techniques and bring down this overhead from order of n squared over 4 to order of log n. But now I'm going to show you that we could do something beyond compressed sensing by optimizing the way we sense the signal of interest. This is going to be the focus of this section. All right, for this, we need to acquire CS measurements within the sector of interest. To obtain, let's say, the mth measurement, which is shown by ym here, the transmitter applies the code word P of m at its phased array. So the receiver gets the inner product of the channel matrix and that code word plus the measurement noise. We can equivalently write this measurement as the inner product of the beam space, this one, and the Fourier transform of that code word plus noise. Now, when the transmitter applies one code word, the receiver gets just one measurement. But one linear measurement is not enough to estimate the matrix that we have here. So the question here is that how can we come up with multiple code words to acquire m measurements within the sector of interest? This means that we need to come up with different code word P of 1 up to P of capital M such that all of them illuminate the same sector or they have the same support for their 2D DFD while they result in different measurements. Okay, the idea is to circularly shift the code word at the transmitter that already illuminates the sector of interest. So let's say that the code word P illuminates the sector of interest with a Fourier representation like this. Now, from basic DSP, we know that circularly shifting P changes only the phase in the Fourier domain, not the magnitude, as you can see in these figures. So, all the code words on the left illuminate the same sector, but they weight different directions with different phase. So, this way we can get multiple measurements of the channel. Okay, let's collect the capital M pairs of circular shifts in the set omega, where each pair contains the amount of circular shift along the elevation, and the amount of circular shifts along the azimuth. Now we can acquire the m measurements by applying the circular shifts of p sequentially according to the set omega, as you can see over here. Because of using circular shifts of p to obtain the measurements, we can write the m measurements in the compact form as the subsampled version of the circular convolution of the channel matrix and that code word plus the vector of noise. This is where compressive sensing comes in, because we are acquiring subsampled version of the channel circularly convolved with the code word. So this calligraphic p sub omega denotes the subsampling operator over here. Okay, the idea in compressed sensing is to reconstruct the channel from this compressed version. You could use multiple CS algorithms that are around for compressed sensing recovery, but our focus here is to improve the reconstruction using CS by optimizing the subsampling locations omega. So for us, the set omega contains the set of 2D circular shifts that we apply at the transmitter to the code word P to apply the CS measurements. So let's first see how omega impacts compressed sensing based recovery. For this, we need to understand the idea of PSF, which stands for the point spread function. So PSF determines the level of aliasing artifacts in the beam space due to subsampling. And it's the 2D DFT of a matrix that is 1 in the locations that are within the set omega, and it's 0 in other locations. Now, what if the set omega is such that you sample all the locations? Well, in that case, n omega is an all 1 matrix, and the PSF, where is equal to the 2D DFT of an all 1 matrix here, is a Dirac function. This means that if I'm at a certain beam space location, I create 0 interference to my neighbors. Now, if we have a subsampling regime like the one shown here, this one, we acquire only few entries from the signal of interest. So in this case, PSF is no more a Dirac function, as you can also observe here, but it looks like this one. For our compressed sensing problem, you can see that a component over here, this one, can create interference that is given by the strength of the PSF at these blue boxes. So this interference basically impacts detection of beam space components within the sector of interest. Our goal here is to minimize the amount of interference that we create at these different blue boxes by designing the set of 2D circular shifts at the transmitter. So, to this end, we formulate an optimization problem you can see here. This optimization problem basically optimizes the 2D circular shifts, omega, applied at the transmitter such that the maximum level of interference that is created to the neighbors within the sector of interest is as small as possible. Okay? And of course, this needs to be solved under the constraint on the number of the measurements. As you can see, this can be solved using integer programming. However, here we propose a suboptimal solution that adds absolutely no complexity for the subsampling design compared to random subsampling strategies. So, here is our solution. We first find the optimal 2D circular shifts, denoted by omega opt here, when the number of the measurements is equal to the sector dimension, which corresponds to the Nyquist regime. For the comb-like sectors we proposed, we showed that the optimal sample pairs for the Nyquist regime looks like the ones that are shown over here. So in this example, we considered an 8x8 phased array and 4 sectors. Okay, therefore, the sector dimension is 64/4, which gives 16. And the optimal 2D circular shifts are the ones shown by the green bubbles. As we can also observe from the magnitude of PSF for the Nyquist regime, the point spread function is 0 within the sector of interest given by these blue boxes. Therefore, the interference within the sector of interest is 0 in this case. Now, For the sub-Nyquist regime, which is the regime that we are interested in practice, the number of the measurements m is smaller than the sector dimension. For this case, we choose to subsample the optimal omega at random. Here is an example of random subsampling that you can see. In this example, we have selected only 8 of the green bubbles at random. As you can see from the PSF, in this regime, there will be aliasing artifacts within the sector of interest that are given by the strength of the point spread function at these blue boxes. But on average, our proposed 2D circular shifts will have smaller aliasing artifacts within the sector of interest than the fully random method. This can be observed from the CDF of the maximum level of PSF within the sector in this picture over here. Here, the red curve, this one, shows the CDF of the maximum level of interference within the sector of interest with our method, and a sample of 2D circular shifts realized using our method is shown over here. Also, the dashed curve, this one, shows the maximum level of interference achieved by the fully random approach. And here you can see an example of 2D circular shifts realized using the fully random method. Here, I will briefly discuss why a good design for the weights is the one that results in a uniform illumination of the sector. For this, let's consider the comb-like illumination pattern we saw earlier in this talk, where it has a non-uniform illumination pattern shown by different colors. And let's say that Dmax over here is the highest illumination strength and Dmin is the smallest illumination strength. In other words, Dmax is the value of an entry of this matrix, this one, that has the maximum value, and Dmin is the value of an entry of this matrix, the same matrix, that has the smallest non-zero value. Okay? Now, in reference 1 over here, we showed that for a noiseless setting, the sparsity level that can be successfully detected by the OMP, this one, which is shown by K here, is upper bounded by this value over here. So in this upper bound, mu corresponds to the mutual coherence of the CS matrix that is equal to the maximum absolute value of the cross correlation between normalized columns of the CS matrix. As you can see, the highest sparsity level that can be detected depends on Dmax and Dmin. And you can see that this upper bound is maximized when Dmax is equal to Dmin, or equivalently when we have a uniform illumination pattern. Now, assuming a successful support recovery by the OMP, we also show that the mean square error, or MSE, of the reconstructed signal is upper bounded by this quantity over here. Okay? So, in this quantity, rho is proportional to the noise level, and again, it can be verified that the upper bound on the MSE over here is minimized when we have a uniform illumination pattern. These observations suggest that uniform illumination patterns within the sector could result in a better reconstruction than the ones with non-uniform illumination pattern. For more details on the proof, you can refer to our conference paper in reference 1. For the simulations, we considered a 32 by 32 one-bit phased array at the transmitter operating at a carrier frequency of 60 GHz. In prior work, people actually did look at the in-sector compressed sensing problem, but they use random code words that kind of illuminate the sector in a greedy way, which means that we end up with leakage effects outside the sector. Therefore, because they focus power poorly, you end up with poor performance. Because of that, as you can see from the figure on the left, our proposed method with RCS and random weights, shown with the green curve, this one, achieves a better normalized in-sector MSE than the benchmarks. Now, by further optimizing the weights to achieve a uniform illumination within the sectors, the red curve, this one, shows that we can get an additional improvement of about 4 dB in normalized in-sector MSE. Finally, by adopting our optimized sampling scheme, our method with PCS, which is shown by this black curve, okay, can outperform our method with RCS. Now, a similar performance improvement can be seen for the data rate using our proposed methods compared to the other methods. So, to conclude, today we learned why standard CS solutions for beam alignment in 5G systems fails. We now know that the real reason for this failure is that the code words used in standard compressed sensing illuminate the beam space almost everywhere, which leads to a poor received power. Then we looked at how to construct our special comb-like sectors that collectively illuminate the entire beam space. An interesting thing about our contribution in sector design is that our sectors can be realized with extremely low resolution hardware, such as 1-bit phased arrays. Finally, we learned that random circular shifts result in aliasing artifacts that are spread out all over the place in the beam space. Also, as we saw, our optimized circular shifts for the proposed comb-like sectors result in a lower aliasing artifacts within the defined sectors than the fully random subsampling method. This is while our method has the same complexity as the fully random approach. Now, the takeaway message of this talk is that the ideas underlying in sector CS can be used in applications that need to estimate some part of a sparse signal earlier than the other parts, like in MRI. For instance, we can think of an emergency situation where a doctor needs to have an MRI scan of the brain of a patient, but based on the records of the patient that the doctor has, the doctor needs to have the scan of, let's say, a certain part of the brain first to take the necessary actions. In such a case, instead of scanning the whole brain, which takes a lot of time, he or she can just scan that certain part using the in-sector compressive sensing. Thanks for watching my talk.
So, I'd like to conclude this talk by advertising some of the open positions in my research group here at TU Delft. In my group, we are actively looking to hire candidates with a strong background on signal processing, with a focus on applications such as communications and sensing. We also work on some exciting research directions that are at the intersection of robotics and signal processing. If you are interested in any of these topics, feel free to reach out to me. My email is shown over here, and we are basically looking to hire a research engineer, a couple of PhD students, as well as a postdoctoral scholar to work on these topics. Thank you for watching and have a nice day.